Dear students, welcome to SRK online classes. Today we are discussing about the characteristic property of transist elements. One of the characteristic property of transist elements, that is variable oxidation states. I'll repeat once again. Today we are discussing one of the important characteristic property of transist elements, which is variable oxidation states. First we'll discuss about what are transist elements. After that, we'll discuss about the characteristic properties of transist elements or D block elements. Definition part of transist elements is those elements in which two shells are incomplete are said to be transition element. I'll repeat once again. Those elements in which two shells are incomplete are said to be transition elements. There are few elements in which only one shell is incomplete. Still it is called as a transition element. I'll give one example. Copper. Atomic number of copper is 29. Electronic configuration is argon. 3d10 and 4s1. In this one, only the outermost shell is incomplete. Therefore, it cannot be called as transition element. But we know that copper group is called as typical transition elements. There is second definition for transition elements. What is that second definition? According to this definition, the elements in which minimum one unpaired electron is present in the d orbital, either in the ground state or in the prominent oxidation state, is called as transition element. In ground state, there is no unpaired electron in the d orbital. Therefore, it cannot be called as transition element. But in the prominent oxidation state, copper shows +2. How do you get that +2? By loss of 2 electrons. Therefore, argon. 2 electrons are removed. 1 electron is removed from s orbital, another one is d orbital. Therefore, it will be 3d9 and 4s0. In d9 electronic configuration, there is one unpaired electron in the d orbital. Therefore, copper shows transition elements. Definition of transition elements is those elements in which at least one unpaired electron is present in the d orbital, either in the ground state or in the prominent oxidation state, is said to be transition elements. In the ground state, there is no unpaired electron in the d orbital, but in the prominent oxidation state, copper shows one unpaired electron. Therefore, copper group is called as typical transition element. Copper, silver, gold are generally called as typical transition elements. Similarly, I'll take one example. Zinc. Atomic number of zinc is 30. Electronic configuration will be argon. 3d10 and 4s2. Look at here. Only outermost shell is incomplete. There is no unpaired electron in the d orbital. Therefore, zinc cannot be called as transition element. We'll see the second definition part. The prominent oxidation state of zinc is +2. How do you get that +2? By loss of 2 electrons. 2 electrons are removed from s orbital. Therefore, in zinc +2, argon will be argon and 3d10 and 4s0. Even in the prominent oxidation state, there is no unpaired electron in the d orbital. Therefore, zinc group is called as only d block element but not transition element. Zinc, cadmium, mercury are only d block elements but not transition elements. Therefore, the general statement is all transition elements are d block elements, but all d block elements are not transition, which means you take any transition element, the differentiating electron enters in d orbital. Therefore, all transition elements are d block elements, but all d block elements are not transition. Look at carefully here. Zinc is only d block element, neither in the ground state nor in the prominent oxidation state. There is no unpaired electron in the d orbital. That's why zinc group cannot be called as transition elements. They are said to be only d block elements. Now the next point is the characteristic properties of transition elements. All transition elements shows following characteristic properties. Due to unpaired electrons in d orbitals. I'll repeat once again. All transist element shows characteristic properties due to unpaired electrons in d orbitals. What are the characteristic properties? Number 1, variable oxidation states. Number 2, color ion formation. Number 3, magnetic properties. 4, catalyst properties. 5, complex formation. 6, interstitial compound formation. 7, alloys formation. These are the few important characteristic properties of transist elements. Today we are discussing about variable oxidation states of transist elements. Before discussing about the variable oxidation states of transist elements, let us concentrate why transist element shows variable oxidation state, or what is meant by the variable oxidation states. First one, definition part of variable oxidation state. Each element in S block element shows only one oxidation state. If you take an example of lithium, atomic number of lithium is 3, electronic configuration is 1s2, 2s1. Lithium always shows only +1 oxidation state. Similarly, I'll take sodium, atomic number is 11, electronic configuration is 1s2, 2s2, 2p6 and 3s1. Or sodium metal also shows +1 oxidation state. Neat on with the lithium and sodium, all first year group element shows what? +1 oxidation state, which corresponds to the group number. Similar manner, if you take an example of second year group elements, all second year group elements shows +2 oxidation state. Means S block elements are restricted to the oxidation state, which corresponds to the group number. If it belongs to the first group, it shows +1. If it belongs to the second group, that shows +2. But whereas in case of transist elements, they shows variable oxidation state. Each element shows minimum 2 oxidation states. Therefore, if an element shows more than one stable oxidation state, it is said to be variable oxidation states. The reasons for the variable oxidation state is, if you take an example of S block elements, only valency electrons are taking part in the chemical reaction. Therefore, their oxidation states are restricted to the group number. But whereas in case of transist elements, for example, I am taking the first member, scandium, atomic number is 21, electronic configuration is argon, 3d1 and 4s. It shows 2 oxidation states. One corresponds to the +2. How do you get the +2? Loss of electron from s orbital. Second oxidation state is +3. How do you get the +3 oxidation state? 2 electrons are removed from s orbital and 1 electron is removed from d orbital. Therefore, it shows +2 as well as +3 oxidation state. That means transition element shows variable oxidation state due to, what is the first reason? Participation of electron from the outermost as well as penultimate electrons, due to which they shows variable oxidation states. The question is, why the penultimate electrons are taking part in the chemical reactions in case of transist elements? Why not in case of S block elements? Even in the S block elements, after losing this electron, still 2 electrons are there. If they are participated in the chemical reaction, definitely that shows variable oxidation state. But it is not possible. But whereas in case of transist elements, valency as well as penultimate electrons, both are taking part in the chemical reaction. Reason for that one is, in case of transist elements, the energy difference between outermost and penultimate shell is negligible. Means the energy difference between 4s and 3d orbital is negligible. Therefore, both the shell electrons are taking part in the chemical reaction. That's why they shows variable oxidation state. But whereas in case of S block elements, the difference between outermost and penultimate shell is more. That's why penultimate electrons are not taking part in the chemical reaction. But whereas in case of this one, both are taking part in the chemical reaction because the energy gap is negligible. Third important point, successive ionization potential differs by less energy. What is the meaning of that one? In case of S block elements, if the first ionization potential is 5 electron volts, second one will be 15, third one will be 60. This gap is more. But whereas in case of transition element, if the first ionization potential is 5 electron volts, second one will be 8 electron volts, third one will be 15 electron volts. This gap is very, very less, due to which outermost as well as penultimate electrons both are taking part in the chemical reaction. That's why they shows variable oxidation state. I'll summarize all the three important points of variable oxidation state. And repeat once again, transition element shows variable oxidation state due to number one, participation of electron from outermost as well as penultimate shell. Number two, the energy difference between the outermost and penultimate shell is negligible. Number three, the successive ionization potential differs by less energy, due to which all transition element shows variable oxidation state. Let us concentrate the variable oxidation states of 3D series elements. So, we'll discuss about 3D series elements. So these are the variable oxidation states of 3D series elements I have given. Look at here, scandium, titanium, vanadium, chromium and manganese. First we'll discuss about the first five, then we'll go for the 12. Atomic number of scandium is 21. Electronic configuration is 3d1 and 4s2. Just now I have given outermost as well as penultimate electrons are taking part in the chemical reaction. That's why scandium shows two oxidation state. One corresponds to the +2, loss of electron from s orbital. Another one is +3, loss of electron from s2 as well as d orbital. Both electrons are taking part. That's why it shows +2 as well as +3. Similarly, titanium. Atomic number 22, therefore 3d2 and 4s2. Atomic number directly corresponds to the valence electrons or d orbital electrons. 22 means 2 electrons. 21, 1 electron is present in the d orbital. Here, 2 electrons are removed from s orbital, forms +2. 1 electron is removed from d orbital, forms +3. Another electron is removed from d orbital, forms +4. Therefore, 3 oxidation states are possible, +2, +3, +4. Look at the next one, vanadium. Here, +2, +3, +4 and +5 oxidation states are possible. Now, the next one is chromium. Chromium shows an abnormal electronic configuration. Remember, in 3D series elements, D4 configuration is not possible. And D9 configuration is also not possible. Except these two remaining, you have to write as it is. Therefore, here I have not represented D4, I represented D5, which is anomalous or abnormal electronic configuration, 3d5 and 4s1. One electron is removed from the outermost shell, +1. All the electrons are removed, it shows +6 oxidation state. Similarly, manganese. Atomic number is 25, 3d5 and 4s2. Total 7 electrons are there. See, I have done all the 7 electrons. +2, 2, +7 oxidation state. After that, next one, iron. Though it is having 8 electrons, but +8 oxidation state in 3D series element is not possible. Maximum will be +7, that is given by manganese. Because after manganese, size of iron decreases. In a period left to right, as atomic number increases, size decreases. Due to small size, you cannot remove all the 8 electrons from iron. Maximum it shows +6 oxidation state. Next one, cobalt up to +4, nickel +4, copper +1. Once again, look at the copper. Anomalous electronic configuration is there. +1 due to loss of electron from s orbital. +2 electron from s as well as d orbital is taking place. And zinc shows +2. If you observe clearly, the total 3D series elements, only one element cannot show variable oxidation state, that is zinc. Variable oxidation state is the characteristic property of what? Transition elements, but not D block elements. Zinc, cadmium, mercury are only D block elements. That's why they cannot show variable oxidation state. Remaining all transient element, they shows variable oxidation states. So except zinc, remaining all 3D series element shows more than one oxidation state, which is called as variable oxidation state. Now look at carefully the first part of this one. Here, though it forms two oxidation states, plus 3 will be the most stable and plus 2 is highly unstable, and in some books it is given there is no plus 2 oxidation state for scandium. Scandium plus 2 oxidation state is highly unstable, and the stable oxidation state is plus 3. And remember, only one D block element which cannot show plus 2 oxidation state is what? Now we can write scandium, which is highly unstable. That point you are supposed to remember. And stable oxidation state of scandium is plus 3. Loss of electron from S as well as D orbital. Now look at the next one. Titanium plus 4 is the most stable. And vanadium plus 5. Chromium plus 1 plus 6. In addition to that, plus 3 is abnormal. Plus 1 is due to loss of electron from s orbital, which has d5 configuration. Plus 6 is d0 configuration. In addition to that, abnormally, even plus 3 oxidation state is also stable. Why this is stable, we'll discuss separately. So, chromium stable oxidation states are plus 1, plus 3, and plus 6. If you look at carefully, in the first 5 or 4, stable oxidation states are due to what? D0. But whereas in case of chromium and manganese, manganese stable oxidation state is plus 2 as well as plus 7. Plus 3 is due to what? Loss of electron from s orbital, which has d5 configuration. Plus 7 is what? Loss of electron from s as well as d orbital. D0 configuration. This one is d5 configuration. One is half filled, second one is vacant orbital. Both are stable. We have already learned vacant orbitals and half filled and completely filled orbitals are relatively more stable. That's why we can explain plus 2 as well as plus 7. Now come to that iron. Iron shows different oxidation state. Majority of compound shows plus 2 and plus 3 oxidation state. Still, plus 6 is also possible, but not plus 8. Though it is having 8 electrons, all 8 electrons cannot be removed. It shows up to only plus 6 oxidation state. Now, which is stable? Plus 3 oxidation state. Why plus 3 is stable? 2 electrons are removed from s orbital and 1 electron is removed from d orbital, d5. Half-filled orbitals are stable. That's why iron stable oxidation state is plus 3 due to d5 configuration. Then cobalt plus 3, which is abnormal. Nickel plus 2, which is abnormal. Copper plus 2, which is abnormal. In addition to this plus 2, even it shows plus 1, that is because of the completely filled d orbital. In case of zinc plus 2, that is d10 configuration. What is the conclusion here? Stable oxidation states possess either d0 or d5 or d10 configuration, except for three elements I have given. Chromium abnormally plus 3 I have given, cobalt plus 3 I have given, nickel plus 2 I have given, and copper plus 2 I have given. These 3 are exceptional cases that can be explained on the basis of splitting of d orbitals. Now, we'll generalize few important points. Now listen carefully. What are the common points in the variable oxidation states? Number 1, except zinc, remaining all elements shows plus 2 oxidation state or more than 1 oxidation state. Therefore, variable oxidation state is the characteristic property of transition elements. Right. The stable oxidation states possess either D0 or D5 or D10 configurations, except a few elements I have given. Half-filled, vacant orbitals, and completely filled orbitals are relatively more stable. Now, we'll discuss about abnormal oxidation states of cobalt, nickel, and copper. Before that, let us summarize all the important points. First point, what I have given is zinc is the only one element which always shows only one oxidation state, that is plus 2. Because it's a D block elements, variable oxidation state is a characteristic property of transition elements but not d block elements. That's why it shows only 1. Second important point is all 3D series elements shows what? Plus 2 oxidation state common, except scandium. It shows plus 2, but scandium plus 2 oxidation state is unstable. Third important one, maximum oxidation state in 3D series elements is manganese, that is plus 7. Minimum oxidation states are observed for 2, chromium and copper, because of anomalous electronic configuration, that is plus 1. Here also plus 1 is there. There is a normal oxidation state of chromium and copper. Next important point is the stable oxidation states of scandium, titanium, vanadium, chromium, manganese are plus 3, plus 4, plus 5, plus 6 and plus 7 due to D0 configuration. Whereas chromium also shows plus 1 and plus 2 oxidation state due to D5 configuration. Now we'll discuss about the stable oxidation state of cobalt. I have given cobalt plus 3, which is exceptional case. That we'll discuss here separately. Cobalt atomic number is 27. Electronic configuration is argon 3d7 and 4s2. Originally, D5 configuration is possible with plus 4 oxidation state. But what I have given is plus 3 is more stable. How do you get the plus 3? By loss of 3 electrons. 2 electrons are removed from s orbital and 1 electron is removed from d orbital. Therefore, cobalt plus 3 will have argon 3d6 and 4s0. Neither it is d0 or d5 or d10 configuration, but still it is more stable. Stability of cobalt plus 3 cannot be explained on the basis of ground state. It can be explained on the basis of splitting of d orbitals. Now I write the splitting of d orbitals here. Ground state, all d orbitals are degenerate orbitals. 6 electrons are there. 1, 2, 3, 4, 5 and 6. Neither it is half filled or completely filled. Now this splits into 2 sets in presence of magnetic field or when ligand approaches. One set is having 3 orbitals. This is T2G orbitals. Another set is having 2 orbitals, which is EG orbitals. We have already discussed this in color property. These 3 orbitals are nothing but dxy, dyz and dzx. Here these 2 orbitals are nothing but dx square minus y square and dz square. In dxy, dyz, dzx, lobes are in between the axis where repulsions are minimum. Whereas in EG orbital, lobes are on the axis where repulsions are maximum. Now 6 electrons are available. According to Hobsbawm's principle, electrons are filled in different orbitals, the increasing order of their energy. Therefore, these 6 electrons are first filled in T2G orbital, first half filled, then pairing will be taking place. We know that half filled and completely filled orbitals are more stable. But here half filled D5 is not possible. Here what is that? Completely filled T2G orbitals are taking part. Now look at here, all orbitals are completely filled. That's why cobalt plus 3 is stable. I'll repeat once again. Stability of cobalt plus 3 is due to what? Completely filled T2G orbitals. It is not D5 configuration, it is not D0 configuration or D10 configuration. It is abnormally completely filled T2G orbitals. Now, same manner we can explain nickel stable oxidation state. I am writing the nickel here. Nickel atomic number is 28. Electronic configuration will be 3d8 and 4s2. Plus 2 oxidation state is stable. Therefore, I write nickel plus 2. Nickel plus 2 is due to loss of electron from s orbital. Therefore, it has 3d8 configuration. 8 means 6, 7, 8. 8 electrons are present. 6 are present in the T2G orbital, remaining 2 are present in EG orbital. Now, nickel plus 2 is stable because of what? Half-filled Eg orbitals. Cobalt plus 3 is more stable due to what? Completely filled T2G orbitals. These two are abnormal, which cannot be explained to the basis of ground state electronic configuration of either nickel or cobalt. Exceptional cases are given. Now come to that copper. Copper is also unique. Let us discuss the unique properties of copper here. Atomic number of copper 29. Electronic configuration is argon 3d10 and 4s1. Copper shows two oxidation states. One is copper plus 1, another one is copper plus 2. How do you get this plus 1? Electronic configuration of copper plus 1 is 3d10 and 4s0. Completely filled orbitals are more stable. But here copper plus 2 will be argon 3d9 and 4s0. See the abnormality. Neither it is d5 nor d10 or completely filled T2G or half filled Eg set of orbital. Still copper plus 2 is stable. That can be explained in the base of high hydration energy. Copper plus 2 is stable in presence of water. Copper plus 1 is stable in absence of water. Anhydrous condition, copper plus 1 is stable because of the completely filled d orbitals. In presence of water, copper plus 2 is stable. In presence of water, hydration energy of copper plus 2 is more. That stabilizes the copper plus 2 ions. In presence of water, it undergoes disproportionation like copper plus 1 and plus 1 are stable. Now in presence of water, it undergoes copper plus 2 and copper. Copper plus 1 is converted to copper plus 2. Both. So therefore, this is called as what? Disproportionation. Simultaneous oxidation reduction of same element is called as disproportionation. Because of the disproportionation, copper plus 2 will be stable. So that is about D block elements, variable oxidation state. I'll just summarize the important points. In 3D series elements, the stable oxidation state or the common oxidation state is plus 2, except scandium. Only 3D series element which cannot show variable oxidation state is zinc, because it is a D block element. Maximum oxidation state in 3D series element is plus 7, which is observed for manganese. And stable oxidation states of 3D series elements is scandium is plus 3, titanium is plus 4, vanadium is plus 5, and chromium is plus 6 because of D0 configuration. Manganese is plus 7, that is also D0. Apart from that one, the stable oxidation state possesses either D0 or D5 or D10 configurations. Apart from this one, few exceptional electronic configurations or oxidation states are observed for transition elements. In case of cobalt, I have given plus 3 because of the completely filled T2G orbitals. Second one, what I have given is nickel is plus 2 because of what? The half-filled Eg set of orbitals. Copper shows plus 1 comma plus 2 oxidation state. That is just because of copper plus 1 is stable in absence of water. Copper plus 2 is stable in presence of water. So this is just because of the disproportionation reaction. And apart from that one, I want to give another 3 important points here. First one, in 3D series, 4D series and 5D series. 3D series, maximum oxidation state is plus 7. 4D is plus 8. 5D is plus 8. In 3D series, that shows manganese. Here it is ruthenium. Here it is osmium. Now, compound is KMnO4, potassium permanganate. Here it is ruthenium tetroxide. Here it is osmium tetroxide. 3D maximum is plus 7. 4D is plus 8. 5D is plus 8. So compounds are manganese, ruthenium and osmium. Apart from this one, in metal carbonyl complexes, the oxidation state of metal is considered to be 0. Here I am writing 1 or 2 examples. Nickel tetracarbonyl complex, in which the oxidation state of nickel is 0. Iron pentacarbonyl complex, in which oxidation state of iron is 0. That means in metal carbonyl complexes, oxidation states of metal is considered to be 0. So these are the few important points related with variable oxidation states of 3D series elements, which resembles 4D as well as 5D series elements. So those are the few important characteristic properties of transist elements. If you like this video, please share this video. Thank you very much. Sir, our conference with